Hey there, welcome to another video. In this video, I am going to talk about the floating point arithmetic. We all have been taught in our school 0.1 plus 0.3 is equal to 0.4. Similarly, 0.2 plus 0.4 that should be equal to 0.6, 0.6. Let us do the same trivial mathematics in Jupyter Notebook in Python here. It is true, very well. So what we have been taught in school, now it has been validated by the computer as well. Second, 0.2 plus 0.4 is equal to 0.6. Mind it, here I have given here two equal to signs which check for the equality, not for assigning, and output here is false. So were we taught incorrect in school, or is the computer wrong? What is the issue here? So let us understand this. We all know that computer stores everything into binary number format. In our day-to-day life, we use decimal number format, which has got 10 digits, 1 through 9 and 0. Unlike decimal numbering system, binary numbering system, it has got only 2 digits, ones and zeros. So in decimal, let us talk first about the decimal numbering system. In decimal number systems, there are numbers which are like 10, 20, 25, 1050, 1 million, 1.5 million, or whatever you want to call. So these all numbers are called integers. On the other hand, we have got fractional numbers, something like that: 1 divided by 2, 2 divided by 5, 3 divided by 10, and so on. So these integer numbers like 1, 2, 5, 10, 20, it can be represented in binary very easily. You just need to keep dividing them by 0. I will show it to you in a minute. On the other hand, fractional numbers like 1 divided by 2, 2 divided by 5, 1 divided by 3, 3 divided by 10, etc., etc. These can be represented like 1 divided by 2, it can be written as 0.5. Here you see 2 divided by 5, it can be written as 0.4. So here we have got three distinct parts: 0, something which is onto the left hand side of the decimal, and 5 which is onto the right hand side of the decimal. Remember this fact. But there are certain fractional numbers in decimal number systems which you cannot represent exactly like this. For example, if I say 1 divided by 3, here you see 0.33333. No matter how long you keep going on, you will never be able to reach till the end. Similar is the case like 1 by 6, 1 divided by 6. You are getting output 1 0.166666666. It will keep going on. You will not never be able to divide it completely. Similar is the case with the binary numbering systems as well. In the binary number systems, the integer numbers can be represented very easily. So if I have to represent 5, as I said earlier, and into binary number system, we keep dividing it by 2. Let me quickly jump onto my Excel sheet here. And if you see it over here, 5. So I divide it by 2. So 2 times 2, that is 4, and we are left here with remainder 1. Now the quotient is 2. We again divide it by 1 time, and we are left with integer remainder 0. So binary of 5 is 101. So we need to keep dividing the number by 2 till the time we are left with zeros and ones only. Similarly, if I go back to here, 1 upon 3, you can never write. So in fact, even in decimal numbering systems, you can write here. If you can see it like this, you can write only those numbers perfectly which are, if I can unhide it very quickly, where the denominator is the multiple of 2 and 5. So anything, any number where the denominator is the part which, like this, 20 here, 2 here, 4 here, 10 here, or 3 here, and numerator is the part above the this thick line, 1, 2, 1 here, 3 here, these are numerator. So you can write in perfect decimal forms in decimal numbering systems only where the denominator is a multiple of 2 and 5. No other number can be written. So similarly, in binary numbering system, if we have to convert a fraction into binary, what do we do? We have to keep multiplying it by 2. But till how long? I will explain. So first of all, if I take 0.1, we multiply it by 2. So we are getting 0.2. So we take the, again as I said earlier, we have got here two parts, 0.2. So it can be written as a 0 point and 2. I have put this decimal into red color to make it distinct. So we have got three distinct parts, one on to the left hand side of decimal, the decimal itself, and on to the right hand side 2. So we, what we do is that we multiply 0.1 by 2, output is 0.2. We take 0 which is onto the left hand side of the decimal and put it here, and now we are left with zero point 0.2, and again we multiply zero point 0.2 or 0.2 by 2 and we get output 0.4. Again same stuff, we take 0 which is onto the left hand side of the decimal, put it over here, and we are left with zero point 0.4 onto the right hand side. We multiply 0.4 by 2, we get the output 0.8. We take the 0 which is onto the left hand side of decimal, put it aside, and we are left with 0.8. Multiply 0.8 again by 2, we are getting output 1.6. We take 1 and keep it here, and now we are left with 0.6 again multiply it by 2. So keep repeating this process till the time onto the right hand side we get 0, onto the right we get 0 onto the right hand side of the decimal. So if you notice here, when we are multiplying it, if I can put it into a color scheme and different color, let me put it over here, something like this. Oh no, not a good choice of color. Let me put it in yellow, which is, so you see this pattern is repeating now. So no matter how long we keep it multiplying it by 2, we are never going to get 0 onto the right hand side of the decimal. So the binary of 0.1, it is something like this, 0 0 0 1 1 1 0 0 1. Of course there will be a point beforehand. So this is how we convert it into, so point triple zero 1 1 double 0 1 1, again double 0 1 1. It will keep going on, it will be repeated. We can never actually get 0 at the right hand side of the decimal here. So there is a limit to it, how long you can go, and there the computer makes an approximation depending upon the memory of the computer. Same is the case with 0.2. If we try to convert it into decimal, again if I can put a color here, here you see again the same pattern is getting repeated. So in a nutshell, what I am trying to say is that it will keep going on no matter how many times you are going to multiply it, and that is the reason computer makes an approximation. Now coming back to my Jupyter notebook here, just like 1 upon 3 we are making, because this will keep going on, we are also making an approximation here, and that is the reason 0 point, if, let me just quickly add something here. So if I just try to write here 0.2 plus 0.4 and print it, here you see I am, what I am getting here is that 0.6, and there are a lot of zeros, and at the end there is 1. it is not exactly 0.6, and that is why it is giving me false. Now the question here is that why this statement is false whereas this statement is true. Again, what is happening here actually is that with some numbers the approximation, it is cancelling each other's error. The approximation error that is happening over here, it is cancelling each other, and that is the reason by coincidence we are getting it here this as true. So in the school we were taught correct and the computer is also correct, and this phenomenon is not only with Python. In most of the languages, computer languages, you will find the same type of arithmetic, and that is the reason you should be very careful with the floating point arithmetic. That is all for this video. If you find this video useful, consider giving it a like, share it with your friends, and subscribe to my channel. Till that time, happy coding.